Chapter 3, Equilibrium of a Particle. Okay, now we start with a very important chapter which will be a continuation of chapter number 2, that was in which we have done about all forces and various types of force systems we studied. Here in equilibrium particle, number 1 is what are the conditions of for equilibrium of a particle. A particle is at equilibrium if it remains at rest or it is moving with a constant velocity. So this is the most paramount condition for a system to be in equilibrium. Okay, now if you see this figure in which we have three forces are acting, one is F1, the other is F2, and the third force is F3. So if this is a condition and if the system is at rest, it is fine, it is considered equilibrium, or if this system is moving this with some constant velocity, it will still be treated as a equilibrium. So what do? We will apply the equations of equilibrium, F1 plus F2 plus F3, and all these forces, if their sum comes out to be equal to 0, then we will say that the system is in equilibrium. So this is a very important condition. And just a reminder from previous chapter, when we say summation of all the forces equal to 0, actually what do we mean by that? If it is a two-dimensional system, remember it will be sigma fx equal to 0 and sigma fy equal to 0. And if we are considering a system in which we have we will say a three-dimensional coordinate system, then along with sigma fx equal to 0 and along sigma fy equal to 0, we will get sigma fz equal to 0. Okay, so I think you have remembered that, and we will again proceed. To maintain equilibrium, it is necessary to satisfy the Newton's first law of motion. As you know, the Newton's three laws of motion forms the fundamental of mechanics, and this requires the resulting forces acting on the particle to be equal to 0. Number 2, the free body diagram. Again, it is very important for all of us to understand the importance of drawing the free body diagram. As in my previous lectures, I also explained that any numerical in mechanics that is given to you, if you understand the numerical and you correctly draw the free body diagram of the system under consideration, it is said that you have solved 50% of the numerical just by drawing the correct free body diagram. So this can be, how could we do it? This can be done by isolating the particles from its surroundings. This is called making a free body diagram. So you have to be very careful when you are drawing this free body diagram systems. Like you can see below, there is classical example of a body of hanging weight. You can see here that there is a fixed system on which a weight is being applied. Okay, so you see a classical example of a hanging weight. There is a body whose mass m is there, and when it is being hanging from a string, you will see the weight of that body will be hanging downwards, and that it will be called as W. But because of that weight, a tension will be developed into that string. It will be equals to tension. Now, if that hanging system is in equilibrium, then this tension must be equal to its weight, and you know what is weight is equals to m times g, where g is the acceleration due to gravity, whose value is a constant, which is 9.81 meters per second square. Now if you look at it, another example over here, there is a spring. A spring is being attached along with, instead of a string, we have about a spring, and the mass m is there. It will have two positions. When there is no weight on the spring, we will call its length is L naught, its original length. But when a weight is being applied on that spring, it will undergo some deformations, and we can call it as like a deformation called S, and the total length we can consume it as L. Okay, so when the spring is there, you know that the spring force will be Fs must be equals to the weight mg, but this spring force will be equal to K times S. It will be K times S, and S is basically the deformation that has undergone into the system. So, and what is K? K is basically the stiffness of the spring. It is the stiffness of the spring, and its value is given as it's symbolized as Newton per meter or Newton per millimeter. And for every material, it will have a unique K. So K is basically the stiffness constant, stiffness of every material. What will be S? S can be very easily calculated as if you know the final length L, you minus it from the original length, which was given as L naught. So it will comes out to be equals to the displacement. Okay, and remember L naught, as I have told you before, it is the undeformed length, and what is L? L is the deformed length. Okay, now if you apply the force equilibrium, now you look at the forces. The forces could be applied along sigma fx, along sigma fz, no, but it is basically, you can assume those forces are acting along sigma fy. So what you do, you apply sigma fy. When you apply sigma fy, you will get fs, which is the vertical force, minus mg, which is the downward force. But what is basically fs going to be equal to? As I told you, it is the spring force. So the spring force will be K times S minus the weight, which is mg. So you could write this equation as Ks minus mg. Why have we taken weight as minus W or minus mg? The reason being, it is applied in the negative direction compared to our positive y-axis. And why is the spring force on the upward side? Because it is along the positive y-axis. You have to be very careful in the units and basically the directions. If you assume the wrong directions, definitely your answer will come, and it will be an erroneous or it will be a wrong answer compared to what you will get if you select the correct directions. So you have to be very careful. And again I am repeating, the most important thing in mechanics, engineering mechanics, in statics and dynamics is to draw the correct free body diagram. And remember what I have told you, if you are able to draw the correct free body diagram, you have solved more than 50% of the numerical correctly. So you have, it means if you have got a 10 marks numerical, you have already been able to get 5 marks out of 10 just by drawing the correct free body diagram. The remaining is your job to get the other 5 marks, because if the diagram is wrong, if the free body diagram is wrong, whatever calculations you will proceed after drawing the wrong free body diagram, they will all be wrong. So you cannot consider that your free body diagram is wrong and your remaining answer will be correct. It will never be the case. Okay, so you have to give very, very critical importance on the free body diagram. Then comes, because we have got a lot of systems engaged into mechanics problems, so sometimes weight problems are there, so we have basically cables, sometimes we have strings instead of cables, sometimes we have got rods being attached, and if you have got cables or if you've got strings, then those strings needs to move freely because of the weight or tension. So they are basically being moved along by means of pulleys. So pulleys plays a very important role in considering how the load is being transferred, how the tension is being transferred. So the cables are assumed to have whatever cables on which the cables are being installed, are being run. We will assume that they will have a negligible weight, even though they have a weight. But why we assume they have a negligible weight? Because that weight is nothing compared to the tensions being developed as a result of the forces being applied by your weight or your system. Okay, and the other important thing, you will always assume while solving the numericals that the cable can only carry tension. You will not assume, because you have two type of forces. You can either have a tensile force, which is the tension, or you can have a compressive force, which is basically a compression. Okay, so what you will do over here is on the first free body diagram, you can see there is a tension. So at T, so there is one T and other T, but that is basically, if you look at it, it is in equilibrium. They will cancel out each other. What about the other free body diagram? The tension T is acting upwards and the weight W, which is equals to mg, is acting downwards. So it is the free body diagram 2. Now what is the procedure for drawing a free body diagram? How would you draw? So number one, very important steps. You have to really be very careful in considering these three steps. Draw the outline shape. You have to look what is the outline shape of this box and table, and what is the box happening? It is lying on the table. So draw its outline shape. Then whatever the forces are being there present on this system, you have to draw those forces. So what is it saying? Show all the forces. And then number 3, identify each forces. You have to show which is what force and which is what force. Like you see, what are the 3 steps I have done? First of all, I have drawn the outline shape of a table, and then there is a mass or some body of box on the table. We put it, so this is the outline shape. Then equal to what you show all the forces. I see one force and I see the other force. The table force is downwards and the other force box is upwards. And then those forces we have defined it as, one is Newton and the other one is basically mg, which is acting downwards. So basically you see those 2 forces, you have shown those forces and you have identified those forces also over there. Then we go to another system which is called as the planar force system. So what does this system means? Coplanar. If you look at it, it means on forces lying on the plane, on the same plane. So for any forces to lie on a plane, plane means at least 2 coordinate axes. So if a particle is subjected to a system of forces that maintains equilibrium, the sum of components on any axis will be 0. Okay, so if you look at it in the figure, you have got F1, you have got F2, you have got F3 and you have got F4. So F1 is lying in the first quadrant, F2 is lying in the second quadrant, F3 is lying in the third quadrant and F4 is lying in the fourth quadrant. So what you will do, you will write and you can clarify it as all those forces are basically converging at the coordinate axis origin. Then F1 you can further consider it as a tensile force. It is F2 is a compressive force, F3 is again tensile, and F4 is compressive in nature. Further, how would you say? You will say summation of all those forces equal to 0, and then what you will do, sum up all the forces x component, you will say sigma fx and then the unit vector I which is being acting, sigma fxi, and then you will sum up all the forces as sigma fyj, which is the forces components which are lying on the y-axis, and then you can segregate it. Since sigma fxi plus sigma fij equal to 0, it means that sigma fxi is also equal to 0, and it also means that sigma fyj components are also equal to 0. In the same way, you can get the resultant also by taking it as under root of sigma fx the whole square plus sigma fy the whole square, and you can also get, once you get the resultant, you also know how to get the direction of your system which is under consideration. Okay, so now we have got the sense of direction of force components must be accounted for by using algebraic signs of plus and minus. So you have to be very careful which force is going to be plus and which force is going to be minus when you perform. For example, if I show you this figure in which what you see are two forces. One force is T force and the other is the N force from the origin. But you look at it, the T forces from the origin, its direction is along the positive x-axis, and the other force, the blue force, its direction is along the negative x-axis. Now if I ask you to perform the force summation of this system, so what you will do, you will write sigma fx is equal to 0, and you will also show the positive x-axis direction which is along the positive x-axis of the graph, that you always have a standard assumption that you have been doing it in the graphs. So exactly you will follow the same approach. So you will write t plus t, sigma fx equal to 0, and you will write plus t and then minus n is equal to 0, and if you simplify it you will see that t is equal to n. So this is a very simple and equation about the x-axis. In a similar way you can also have forces along the y-axis also, and you will but here if the forces are on the y-axis, just imagine it will be not sigma fx equal to 0, but it will be sigma fy equal to 0, and you will see those forces, which force is lying along the y-axis and which force is lying along the negative y-axis, and you perform the respective summation. Now let us give you an example of this system just below it. You will see there is basically a weight, a circular weight hanging. This weight, if you look at it, is W, and then there are two tensile forces acting. Maybe it is a tension, or maybe it is hanging through a cord or cable, passing through a cable. So system, we do not know that, but we cut that system and we see one force is TA and the other force is TB. Now what we will do? We will do is that we need to solve this system, and if we know W, we can say we will be interested in calculating, and if we know theta, we can basically get two equations from this system. since it is a two-dimensional system, the maximum unknowns that we can get from this system will be 2. So how we will write this equation? We can say, for example, if we apply sigma Fy and we say that the positive y direction is acting on the upper side of your coordinate system. So when you do that, you will say Ta sine theta, as you are applying the vertical sigma Fy equal to 0, so you will say Ta sine theta positive, it will be one component. Now you go to the other force or tension, whatever it is. You must remember, if we say tension, if we say force, it is one and the same thing, they are synonymous. So you don't get confused why I say tension or I'm not saying force, or why I'm saying force and not saying tension. It is one and the same thing. Every tension is basically a force, and every force can be treated as a tension in the system. So the other force comes out to be also equals to Tb sine theta. And why they are both positive? Because the components of these forces will be along the sigma y-axis. So these two forces are being resolved along the sigma y. Then is there any other force acting on the y-axis? If I look at it, there is another force, and that force is being the weight. So we add weight also in sigma and y in sigma Fy, because the weight is acting along the y-axis. But Ta sine theta and Tab sine theta, if you look at it, they were positive. What happened to the weight? But weight added, but we have inserted a minus sign. Why a minus sign? Now look at the figure. Precisely speaking, the FBD, the free body diagram. The weight is hanging on the downside. So what does this tells us? It tells us that it will be minus. So the equation generated here is Ta sine theta plus Tb sine theta minus W is equal to 0. This is one equation. Then you have to apply another equation also to solve this system. Remember, you will always, for a two-dimensional coordinate system, you will always apply to generate two equations. One applying sigma Fx equal to 0 and other applying sigma Fy equal to 0, and you will always get in a numerical two unknowns. It can be either Ta, Tb as an unknown, it can be a theta or phi as unknowns, or it can be all given as you can have Ta to be calculated and W to be defined. So unknowns will always be 2 because it is a two-dimensional coordinate system. So apply sigma Fx equal to 0. When you apply sigma Fx equal to 0, what you get? You get Tb cos theta, but this Tb cos theta, we write it as plus Tb cos theta. Okay. Now what other tension is to be applied is a tension for Ta, and its component along the x-axis will also be equal to Ta cos theta. So Ta cos theta, but just like before, but we for the weight, you see where is going to be the cosine theta for Ta? It will be on the negative x-axis. It will be not on the, if you resolve Ta into its two components, by head to tail also you can see, it will be one component along the negative x-axis and the other component will go towards the positive y-axis for Ta. So that is why on the vertical component you see Ta sine theta as positive, but the Ta cos theta is taken as minus. So the equation generated as a result of sigma Fx is equal to Tb cos theta minus TA cos theta is equal to 0. So these two equations are being there. If I could give you any values for theta, you can say theta equals to 40 degrees or 45 degrees, weight equals to, so you say 50 Newton or 80 Newtons. You can easily solve. So you have two unknowns and you can solve. It's basically a simultaneous equation, and two equations are there, two unknowns are there. You can very easily calculate what is the value of TA and what is the value of TB as the unknown, and what will happen is that your system will be solved. Okay, so this is, you have to take, this is a very important slide, and you should study it very carefully. Now we go to another force system, which is a 3D force system. Now we have got our three-dimensional force systems. Okay, as I have told you, remember there is a two-dimensional coordinate system and there is a three-dimensional coordinate system. So here the methodology remains the same. If you look at it, instead of x, y axis, there is another third axis being formed, and this axis makes it a three-dimensional force system. Why? Because there are x, y and z axis being generated. So if you want to look at realistically how they are being formed, practically speaking, if you look at your home, if you look at it, a single room, and you see where is the two walls coincides, so you get a three-dimensional coordinate system. One edge of the wall, the other edge of the wall, and the vertical height of that wall gives you a practical example of a three-dimensional force system. Three-dimensional coordinates are being there, and you can have any forces being generated. So this is a practical example. You will look at it at your own home, one of the, considering any of your rooms. Okay, so you look at it again, it's basically all the forces are converging at a single point, and they are being called as F1, F2 and F3. And how we will solve this system? By simply saying sigma Fx along the IA plus summation of all the forces along the Yj plus summation of all the forces along Zk must be equal to 0. So we will write it as, how we will write it as sigma Fx is equal to 0. We will write it as sigma Fy is equal to 0, and we will write it as sigma Fz is equal to 0. Sigma Fx equal to 0, sigma Fy equal to 0, sigma Fz is equal to 0. This is called as a three-dimensional force system, and individually all those components of xi, same logic will apply. We will add all those components of f1, sigma fx1, sigma f2, sigma fxi plus sigma f2xi plus sigma fx3i equal to 0. Then you go to sigma fyj equal to 0, and you will write sigma f1 y equal to 0, sigma fxyj plus sigma f2yj plus sigma f3yj equal to 0. Then you go to sigma fxz, and you will write sigma f1z k plus sigma f2z k plus sigma f3z k equal to 0. And then you will solve your system by individually taking summation of all the forces. Sigma fxi equal to 0 plus sigma fyj equal to 0 plus summation of fzk equal to 0. You will see it's a bit tricky, but when we will come to the numericals, this will further simplify how we will basically apply this system. Now, very simple example over here is being shown to you about equilibrium of a particle over here. Very simple. You look at it from the heading equilibrium of a particle. It has not occurred any problems. In a second, you will see when the resultant of all the forces in a particle is zero, the particle is in equilibrium, as previously I also explained to you. So one of example, they have shown you that at point A two forces are converging. One is 100 pounds, the other is also 100 pounds. And remember, it is not on neither x-axis, it's not on y-axis, but still, if you look at it from A, 100 pounds and 100 pound forces are cancelling out their effects, and it is in equilibrium. Okay. So another example is being shown over here. If you see the statics of a particle, just below there are like four forces are being acting. At one force is F1, which is 300 pounds. The other force is F2 is 200 pounds. F3 is 200 pounds. F2 is 173.2 pounds, and F4 is equals to 400 pounds. These forces are there, and again they are not specifically telling you about any coordinate system. X and Y axes are over there, but you can apply, if you look at it, you can basically graphically you can also plot these forces from the origin O, like F1 is 300 pounds, then F2 is 173.2 pounds, then you go for F3, which is 200 pounds at an angle of 30 degrees from the negative y-axis, and then the F4 is again converging, and you can see F4 is equals to 400 pounds. So it's basically forming a closed polygon, providing a graphical expression of the equilibrium of point A. To express graphically the conditions of equilibrium of the particle, so we write how we will write it: resultant of equal to summation of all the forces equal to 0, resolving each force into rectangular components sigma fxi plus sigma fyj equal to 0. Okay, so you apply sigma fx equal to 0, sigma fy equal to 0 separately into the system. Now let's say sigma fx equal to 0. They have shown you all the, just below equation 2.15, all those equations have been shown to you, and you write sigma fx is equals to 300 pounds minus, what will happen for the 200 pound force? 200 pound force is minus sine of 30. Remember, it's that component of 200 pounds is in the negative x-axis, and further for the 400 pounds, again it is minus 400 pounds sine 30, because that component, if you resolve it into its rectangular components, it will be on the negative x-axis. So you have 300 pounds minus 100 pounds minus 200 pounds. Now you add up those forces and you will be surprised that it is coming out to be equal to 0. Okay, so the equilibrium is being maintained? No, it's half the equilibrium is being maintained as sigma fx equal to 0. The picture is not complete, it is half solved. The numerical is not complete. You have to apply another equilibrium, which is sigma fy is equal to 0. Now if you apply that, again see what will happen. It will be the force which is vertical equilibrium. It is 173.2 pounds, but a minus sign is there. Why? Because it is on the negative y-axis. Then you apply again for the 200 pound force. It is 200 pounds cos 30, but a minus sign is being generated over there. Okay, then you apply again plus 400 pounds cos of 30, but this one, you look at it, is a positive sign, because you resolve the F4 equal to 400 pound force, that will be lying along the positive y-axis. So they say is plus 400 pounds cos of 30. Now you simplify the values, you add those values algebraically. What you get? 173 minus 173.2 pounds minus 173.2 pounds and plus 346.4 pounds. and to add up algebraically all those values, and you will get it equal to 0. And you see again what happens when you sum up all those forces, the net result is coming out to be equal to 0. Now you tell me why it is 0, sigma fx equal to 0 and sigma fy coming out to be equal to 0, all those forces you are adding. So what does this tells you? This tells you that these forces F1, F2, F3, F4, which are basically being concurrent at point A, it is basically equal to all those forces when are resolved along those sigma fx and sigma fy, they are all in equilibrium at point A. So the necessary and sufficient conditions for equilibrium particle has been achieved and the system has been solved, and you can say that this system of forces acting at point A, the equilibrium particle has been satisfied and it is in equilibrium. So just a brief reminder about Newton's first law of motion. What does it tell you? You have solved it because of the conditions of Newton's first law of motion. If the resultant forces acting on a particle is 0, the particle will remain at rest, originally at rest, or will have move with a constant speed in a straight line. Very important, not in an angular velocity but in a straight line if originally in motion. From this law and from the definition of equilibrium given, it is seen that the particle equilibrium either is at rest or is moving in a straight line with a constant speed. And in the following sections, various problems you will see considering the equilibrium of a particle will be considered. Okay, so this is very simple equations. Before now, in the previous problems, in the previous explanations, we were always doing symbolically like TA, TB, W, but we were not doing it numerically. But this numerical explains to you how you basically apply sigma fx equal to 0 and how basically you apply sigma fy is equal to 0. So this is, now again we proceed, we have basically gotten the fundamental concepts, the theoretical concepts are here. One very simple example is being shown. Now we will go to the pure numericals from the book that I have told you. You also have the solutions being available, and I will basically be some numericals I will try to explain to you in a most simplest of the way so that your concepts are being generated. Okay. This numerical is being given. Find attention. Okay, we will solve this numerical, a very good numerical, which is being basically, if you look at it, it is being hand solved.